We've been looking at the psychophysical methods. We looked a bit at thresholds, and in this video we'll look at another one called magnitude estimation. So this is quite similar in some regards to the difference experiments that we were looking at before, where you had to tell the difference between, say, two weights or two lines. But in magnitude estimation, we're not looking for that kind of minimum threshold. We're not looking for threshold at all. We're not looking for that kind of minimum difference that you can tell. Instead, with magnitude estimation, this was a psychophysical method that looked to see something along the lines of, we'll give a rough example. If you were presented with a light, say, that was of say, intensity 20, whatever that means in this case, and you were told it was intensity 20 and said, okay, just kind of judge this as intensity 20, and then you were presented with a light that was twice as bright. It had twice as many photons or so on. It was twice as bright. We could measure that empirically. Would you estimate that that light had doubled in intensity? Would your perception reflect this, or in fact would you say something else? And in fact, with this, it turns out you would say something else. When the light intensity doubles like this, from say 20 to 40, you'd probably say something like 28. Your impression would be that it's not doubled, it's kind of gone up a bit, but not quite doubled. And we'll see why that is in a moment. And that example is true of vision, but it's different for different senses, as we'll see again in a minute. For something like electric shocks, if you were given some intensity of 20 and then it doubled, and you were asked again, you would in fact say it's double. It's gone way more than double this time. It's like 60 or something like that. You would perceive it as being more intense than the second stimuli. So your estimation of the difference, the magnitude difference between the stimuli in the first experiment and the stimuli in the second one is your estimation. That's the magnitude estimation, what you think the difference is. And now another equation popped out of these studies. There was a lot of work done on this, and the work that came out of it was Stevens' power law. Stevens' power law. And it was Stanley Smith Stevens who kind of drew this up, and he did a lot of experiments that gave a lot of different numbers, the same as in the video previously. We looked at the Weber fraction, which gave us this kind of constant which we could apply to each different sense, i.e. for lifted weights or for brightness. Those constants were different, but we could apply that constant, and he kind of discovered many of these constants for each sense, or for each kind of the magnitude estimation experiments that he tested out. The Stevens power law is slightly different to the Weber function, or the Weber fraction, sorry, because it's a power law, so it contains an exponent. So it looks something like this. We could say, let's use P. Say P is the perceived magnitude that the perceived difference in magnitude that you've attained, and that would be equal to some constant. In the Weber fraction we called our constant K, so why not call it the K here? And then that would be multiplied by the stimulus that you've been presented with. And then this is where our exponent, our power, comes in. That would be the stimulus, that the intensity raised to some power n. And this exponent was the thing that Stevens uncovered as being different for each, for the various senses. I think I have it open here on a web page here. We could see here that for loudness, the exponent was 0.67. So you would do your equation and you would put 0.67 as n. For brightness, it would be 0.33, and so on. For for cold, that's 1. It's interesting to find the ones that are 1, because an exponent of 1 means that your magnitude estimation is correct. It means that you're likely, if it's double the intensity, you're likely to estimate and to perceive that it's double the intensity. I think for line length, is line length on here? Line length, visual length of a projected line. The magnitude was also 1, so that was similar to our Weber fraction in the last video. So I found a graph which I think was derived from Stevens's work here, which shows 2 things that we'll look at, and one is response compression. These are kind of things that drop out of power laws, response compression, and the other is response expansion, and we talked about electric shocks and light in a moment ago, and with light what we have is response compression, whereby what we mean is that for light, if we look at our graph here, if we say that at around, it looks like around 35 or something around there, then the stimulus magnitude is equal to the perceived magnitude. So it's about good there. So we'll begin there. Let's say that you've been given this thing, and so you know that this is the magnitude. Someone presents you with a light of 30 something, 34, let's say, and you say, okay, that's 34. But if that light is then doubled to say 70, then, or 34 times 2, it's about 70, then you won't perceive it as doubling to 70. Instead, it will only go up to, according to this, it would only raise to about 40. Your perceived magnitude would be 40, and the exponent that we derive from this line is 0.33, which was the same as this is listed on our thing for brightness. Yes, 0.33. So n in this equation, if we were using it for light, would be 0.33, and if we plug that in, we would get a line that followed this curve. And the response compression then comes from the fact that you actually perceive the perceived magnitude is less than the actual magnitude. So if you double it, your senses almost kind of dim a very bright light. They lower it down such that if I'm looking at my computer now, it seems kind of so bright, and there are a number of photons kind of streaming from this and hitting my eye. But if I look outside and it's a bright sunny day and there's a bright reflection shining off the pavement, then although that reflection would contain thousands, perhaps more photons, I won't perceive it as being 1,000 times more bright. So it's good for my brain to do this because I won't end up being blinded by something like that. So you get this response compression. Whereas with the electric shock, we have it going the other direction. We have response expansion. So if again it seems to be about even, or at around 30, 35, let's just say it's 35, such that if someone shocked you and said, okay, this is a shock of 35, I'm now going to give you another one, estimate what the magnitude is, for you to perceive a doubling of magnitude, up to 70, they only have to turn it up to about 40. So they only have to turn that magnitude up by 5 units, and that's because, and from that we derive that the exponent for electric shock, the perceived stimulus, is 3.5. So when the exponent is less than 1, we have response compression, and when the exponent is greater than 1, we have response expansion. And you can see here for line length, we actually have a linear result where we perceive kind of no expansion or compression, and we're pretty accurate at that. This law doesn't hold in all cases, and there's some people who debate it, but I just wanted to introduce you to magnitude estimation as a means of studying perception, and then to Stevens' power law, which kind of came from that.